In this video, I want to go over the solutions for Precept 10. So here is the data set that we're working on, so called it brains, right? And what you have here is you have the brain weight and the body weight. And the first question asks us to figure out the basically way to get a linear relationship between the brain weight and the body weight. So here is the final solution, so I'll just modify it a little bit. So the first thing that you would do is you would probably start with just plotting the body weight on the x-axis, and you'd plot the brain weight on the y-axis. And that's because so the x is usually kind of the predictor variable, the y would be the dependent variable, the thing that you're predicting, and intuitively it kind of makes more sense to predict the brain weight from the body weight than vice versa, although it kind of doesn't matter. So here I'm plotting the geom point, and I'm also saying that I want a straight line through all the points, so I'll specify method equals lm to get a straight line. So here's the kind of thing that I get, and what I see is that the relationship is really not linear, right? So this is the best line that ggplot decided to draw, and you can clearly see that it doesn't really describe the relationship between the x and the y all that well. You have all those outliers. It also seems like, you know, the curve maybe would go kind of like this. So if you try different things, eventually you could come up with the idea of, oh, so I'll plot the log brain versus log body and see how that works out for me. And if you do that, that looks a lot nicer. So what you see is that, like, it seems like there's a linear relationship. There may be like a few outliers, but it's not even clear that they're genuine outliers. Maybe it's just that, you know, this one is a little bit far away from the line. So at this point, you would say, good enough, I'll try to run my regression. So before you run the regression, you've got to check all the assumptions. So you make sure that the assumptions for the linear regression are satisfied. And that's because if the assumptions are not satisfied, you can't really run the regression, right? So because kind of the p-values that we'll be computing are not going to be meaningful. So for that, what we'll do is we'll plot all the diagnostic plots. So we'll load ggfortify, we'll make the fit. So here we're predicting log brain from log body. And we'll use autoplot to get the diagnostic plots. So let's look at the diagnostic plots. So here you have residuals versus fitted. So what it means is when you're predicting 4, so the log brain is 4, then here are your residuals. So here's how much you'd be off by. And what you hope is that on average you'll be off by 0, and that you won't be off by too much at any point. So ideally this line would be straight, and it would be straight at 0. So this line is just kind of the median residual, so the median and the average should ideally be 0. Here it's not quite straight, but you don't have like very huge outliers, and you don't have like huge asymmetries here. Although over here there is maybe a cause for concern because most of the residuals are below 0. You have very few that are above 0 when you're predicting a high log brain. So that might be a concern. So especially this point might be a concern. Next, you're looking here, and here you want ideally for the QQ plot to be completely straight. So that would indicate that the distribution of the residuals is normal if it's completely straight, or at least kind of it wouldn't contradict the idea that the distribution is normal. This is really a different version of this. So again, you want kind of like a straight line. Finally, here what you want is you want to not see any large residuals with a lot of leverage. So leverage means that if you take this point out, that will influence the estimate for the coefficient a lot. So you care about points with high leverage, and you don't want points with high leverage to also be outliers. So here, kind of this point, again 46, might be a cause for concern. So the next thing that you might do is you might say, okay, so I have those outliers to some extent, and this one has pretty high leverage. So what are they? Kind of what's going on with them? So we can look at those. So this is the lemur, the dolphin, and the hippo. So one kind of interesting thing is that the dolphin and the hippo are actually phylogenetically pretty close. So the hippo is the closest relative on land of these cetaceans. So we shouldn't read too much into that, because kind of the dolphin is over here and the hippo is over here. So actually kind of we are erring in different directions when we're predicting the log brain for the dolphin and the hippo. So can't draw too many conclusions here. Probably we shouldn't remove any points. So sometimes you might make the case of, oh, like let's just remove the hippo because it's kind of messing things up here. This line would be a lot straighter, probably if the hippo was not here. So you might be tempted to remove the hippo. On the other hand, like if there's not a principled reason to do that, like maybe you have like, you know, biology-based reasons to think that the hippo is like really atypical, then maybe you wouldn't remove it. So here we chose not to do that, although here's how you would do it if you wanted to. And if you have kind of strong reasons to think, like either kind of biology-based, or you might think that this is just like a measurement error or a typo or something, then you might remove this. Okay, so we said, okay, the assumptions are approximately satisfied. If we are happy to say that the assumptions are approximately satisfied, so that means that this is like approximately a straight line, and this is approximately a straight line at 0, and we don't have points that have high leverage and that are also outliers, or at least like not too many of them, then we can proceed. So I should mention that all of this might sound a little bit vague, and the reason this is a little bit vague is because that's the usual practice. People kind of just eyeball things and say, well, like looks okay to me, or no, this looks like really not okay. So there is subjectivity here. So what you should be doing is you should be definitely looking at not having something that's like very far away from straight here, and something that's like very lopsided here. If you see something that's really lopsided, then you say, okay, can't proceed, can't compute the p-value. Possibly, if you're doing the bonus, need to come up with a different hypothesis that doesn't create all those problems. So now let's run the regression. So we actually already computed the fits, so all we need to do is look at the summary. So this is the summary here, and what you see is that the estimate for the coefficient for log body is 0.7. So what that means is that if you're trying to predict log brain, you would say 2.3 plus 0.7 times log body. That's going to be log brain. Now this is the p-value that corresponds to this estimate. So this p-value says basically that's the p-value for the null hypothesis that this coefficient is actually 0. So if this p-value is small, that means that the data is inconsistent with this coefficient being 0. If this coefficient is 0, well, in this case it would mean that the log body is not associated in any way with log brain. But we can actually reject the hypothesis that this is 0 because this p-value is really small. It's smaller than 5%. It's really, really small. So we can reject the hypothesis that this is 0, so we can conclude that there is an association between log body and log brain in this case. So, okay. So sometimes you would fail to meet the assumptions. So here you have kind of an example of that. So if you're trying to predict the litter size from log body, for example, and if you plot this, what you'll see is that kind of here, this is really not straight. So you have like a large outlier in this. You have a point with really high leverage that's also an outlier. Here you have a very large outlier, right? So this is like, so if it's like larger than 2.5, that's really large. So this one, well, you might consider removing it and see what happens, but as it stands, it's really large. The assumptions as it stands are not met, so you can't really run the regression and make any conclusions based on the linear regression model. You might have other models, but you can't really do that here. Okay, here we're treating the letter size as categorical instead. So to check the assumptions here, what we would do is we would do a box plot. And what we see is that kind of what we want is we want for all those box plots to be about the same width, right? So that would indicate that the variance is the same, right? So what this so kind of here the prediction for this category, for the category 2, is going to be for the category 2, kind of the prediction is going to be this, and then this is kind of the spread. So what we want is for the spread to be symmetric, and we want for the spread to be the same for all the categories. So here I didn't actually round, so I'll round the letter size here so that they have fewer categories. And this still gives me kind of some categories where there's like a lot of outliers. So for example, letter size 4, and we don't have a constant, well, the width is approximately constant, but here we have like a lot of outliers. So then instead, so we're saying, okay, can't run the regression here. So instead what we'll do is we'll say, okay, let's make the categories smaller. So let's make 2 categories. So one category is going to be letter size greater than 5, and the other one is going to be letter size is 5 or smaller. So that's going to be my new column in brains. I'll call it L5, and that's going to be letter greater than 5. So we'll make the fit, and here I happen to have checked and seen that log body works a lot better. But if you try to predict log body from this category, so 2 categories, 1 letter greater than 5, 1 letter smaller or equal to 5, then you'll have 2 box plots that look kind of good, right? So they're approximately the same width, so that's good, and they're like, well, you could say approximately symmetric, right? So at any rate, like, this is not like the minimum. So this is not quite symmetric, but kind of good enough. So now we can proceed. So proceed with what? Well, with predicting log body from those 2 categories. So true, meaning letter is greater than 5, and false, meaning letter is 5 or smaller. So we'll do the summary of the fit. And what we see here is that, yes, this is significant, right? So what this means, so because this p-value is smaller than 0.5, so when you're predicting the log body from those 2 categories, the way you would do it is you would say, well, if the category is true, you would predict this minus this, and if the category, if the category is false, you just predict this. And what you see is that we can reject the hypothesis that this number is 0, which means that there is a difference between the 2 categories, which means that we can conclude that there is an association between letter size and the body weight. So that's great. Now we're going to try a different approach, and I should say, if you are actually doing a study, you can try one approach or the other. You don't get to try both. So you don't get to try to run 2 statistical tests. So here what we're going to be doing is we're going to be saying, okay, we have 3 categories, so small letter, medium-sized letter, and large letter. And I'm going to do it like this. So if we look at brains now, you have a column that corresponds to letter size. So here it's like letter size, so here 5 is medium, and then 1.2 is small, and so on. Okay, so before we run the test, we need to actually look at the box plots to make sure that there's no outliers. So here it is. And this is approximately symmetric. There is like 1 outlier here, but it's not too far away. And the widths are approximately the same, so we're fine to run the regression. So let's do that. So if we run this regression, what we see is that we cannot reject the hypothesis that this is 0. We actually cannot reject the hypothesis that this is 0 either, right? So here the p-value is greater than 5%, and 5% is kind of the usual threshold that we use. With that said, we can look at this p-value. So what this p-value is looking at is at the hypothesis that both this and this is 0. And we can reject that null hypothesis. So if we pre-register the null hypothesis that both this is 0 and this is 0, we can reject it, which means that we can conclude that there is a difference between at least kind of 2 categories. So either this is not 0 or this is not 0. Okay, so this would be the f-test. The f-test is useful when your null hypothesis is that all the coefficients except the intercept are 0, possibly are 0. Now, it might be that you are unlucky and you pre-registered the null hypothesis that small letter size is different from medium letter size and large letter size, right? And that you could not reject because the p-value here is greater than 5%, which means that you can't reject the hypothesis that this is equal to 0. Okay, so to repeat, so the difference is for the f-test, the null hypothesis is that nothing matters. The null hypothesis is that this is 0 and also this is 0. So according to the null hypothesis, if you're trying to predict the log body weight from the letter size basically doesn't matter. You'll predict the same thing every time. You'll predict the intercept. On the other hand, for those kind of t-tests, what the null hypothesis is this is 0 and the p-value for that is here. And the null hypothesis for this estimate is that this is 0 and the p-value that corresponds to that is over 0. And that is how you would usually do things. So the f-test just in general tells you something is going on with one of the variables.